In this video, we're going to be learning about how to take derivatives using the chain rule. The chain rule can be used to find the derivative of composite functions. So the derivative of f of g of x is equal to f prime of g of x times g prime of x. You can basically think of the chain rule as the derivative of the outer function times the derivative of the inner function. As a tip, sometimes it can be difficult to determine what the inner function is. You want to try and look for some sort of grouping mechanism that the function is inside of. So some examples of this might be like parentheses, a radical, an exponent, or a denominator, for instance. All right, let's take a look at some sample problems. In A, if h of x is f of g of x, determine f of x and g of x. Then find the derivative of h of x using the chain rule. All right, so I can see the inner function here is 2x plus 4. So I'm going to say that g of x is 2x plus 4. And the outer function, what's on the outside of the grouping mechanism, the outside of the parentheses, that's sine, and we always need a variable in there, so sine of x. Let's check this. If I want to see that if f of g of x does produce h of x, I'm going to take the function of g, plug it in for x into f of x, basically substitute it in, and you'll see I get sine of 2x plus 4, so we have broken apart the composite functions correctly. All right, now let's actually take the derivative of it. So h prime of x, the derivative is the derivative of the outside. The derivative of sine is cosine, and we're going to keep that inner function the same. But what we're going to do is we're going to multiply by the derivative of it. So the derivative of 2x plus 4 is 2. And we can rewrite that just simply by putting the 2 in front as a coefficient. Okay, for B, we're going to do the same exact thing, except our function is now different. H of x is the square root of 3x. So we can see that the inner function, what is inside the grouping mechanism, is 3x. So g of x is 3x. That means f of x is equal to radical x. And if I compose these functions just to check, I'd be taking 3x, plugging it in here, and we can see that that works. Okay, now that we have confirmed what f of x and g of x are, let's actually take the derivative. Before I do that, I'm just going to rewrite this as 3x to the 1/2 power because that will help us take our derivative a little bit easier. Okay, so the derivative of the outside has an exponent or a power of 1/2. So we're going to use the power rule. So 1/2 times 3x to the negative 1/2. You're always going to keep that inner function the same when you're doing the derivative of the outside, and then times by the derivative of that inner part. All right, I'm going to clean this up a little bit here. So I'm going to just merge this into one fraction and get a radical back in there. So this looks like 3 over 2 times 3 radical x as our derivative of h of x. All right, for the rest of the practice questions here, we are not going to identify the two functions. We're just going to now take the derivative. All right, number 1, on the outside, I have a 7. So when I take the derivative of the outside, I'm going to be bringing that power down, subtract 1 from the exponent, and multiply by the derivative of the inside. So notice for derivative of the outside, I brought the 7 down and subtracted 1 from the exponent, and then multiplied again by the derivative of the inside, which is 5. We could clean this up slightly by just changing this to 35 times 5x to the 6th. Number 2, the derivative of the outside, so the derivative of cosine is negative sine. Keep the inside the same, but we are going to multiply by the derivative of the inside, which is 2x minus 8, and there is our derivative of g. Number 3, h of x is equal to ln of 8x plus 3. Okay, derivative of the outside, the derivative of ln is 1 over whatever you're taking the natural log of. And then we're going to times that by the derivative of the inside, which is 8. And if we want, we can rewrite this as 8 over 8x plus 3. Number 4, f of x is equal to negative 3 cosecant 4x. All right, when we take the derivative of the outside, this one's a little bit tricky. The derivative of cosecant is cosecant cotangent, or negative cosecant cotangent. So I'm going to multiply by that. I'm going to bring the negative 3 down. The derivative of cosecant is normally, so I'm going to put in parentheses here, negative cosecant cotangent. And then we're going to multiply by the derivative of the inside, which is 4. Let's notice here we have some things that we could simplify. Let's multiply all of these coefficients, and we are going to get positive 12 cosecant 4x, cotangent 4x. Again, one big idea that you want to focus on as you're using the chain rule is that whatever was initially in the inside, make sure it stays there when you take the derivative of the outside. All right, for number 5, I am going to just rewrite this as 2x to the negative 10th. Okay, that way I'm looking at this as a negative exponent rather than a denominator. When I take the derivative of the outside, it reminds me of a previous question we've seen already in this video. We're going to bring the exponent down, subtract 1 from it. Notice that's going to be negative 11. We're subtracting 1 times the derivative of the inside, which is 2. Okay, I will be cleaning this up a bit. So this is going to give me negative 20 over 2x to the 11th. I'm going to make that exponent positive. Since the question was formatted with a positive exponent rather than a negative one, I'm going to try and format my answer the same way and kind of mirror that formatting. Number 6, taking the derivative of g of x equals e to the x squared plus 3x plus 2. The derivative of e to anything is itself. Or I should say the derivative of e to the x is itself. Now what we're going to do is we're going to multiply by the derivative of the inside, which is 2x plus 3. Sometimes people look at this and they don't see the inside. There's no obvious grouping mechanism like a parentheses or a radical. So we can think about parentheses around this whole exponent if you want. And now you can see that that x squared plus 3x plus 2 was basically substituted into the function e to the x. For 7, p of x equals the cube root of 4x squared plus 3x. Before taking the derivative, I always rewrite my radicals so that they have a rational exponent. So I'm going to rewrite this to the 1/3 power. Let's take the derivative of the outside. The outside has an exponent or a power. So using the power rule, we bring that down and we subtract 1 from the exponent. And then we're going to multiply by the derivative of the inside, which is going to be 8x plus 3. As I mentioned before, we're going to try and mirror the formatting of the question. So I'm going to rewrite some of this here. In the numerator, I have 8x plus 3. In the denominator, I have a 3. And then I also have the cube root of 4x squared plus 3x squared. When you are rewriting this, only the part that has the negative exponent, so that's in this case the 4x squared plus 3x, is moved to the bottom. Okay, the 3 was already in the bottom. That's why it stays where it is. The 8x plus 3 was just like a numerator or a regular term, so we're just going to keep it in the numerator there. All right, for number 8, this one looks different from any of the others we have seen so far. So it's y equals x squared times cotangent of 9x. So I want you to think for a second before I explain what to do here. Why is this one different from all of the others that we have seen? Okay, so think about that for a second. And hopefully you're noticing it's because that we have a function times a function. We basically have x squared times the cotangent of 9x. And this basically is going to be now an application of the product rule. So yes, it is possible that in one question, you're using product rule and chain rule, okay? Think about the others we've seen so far. We've seen power rule with chain rule. Now we're just combining product rule with chain rule. Okay? All right, so we're gonna find the derivative of y here. And when I do product rule, I like to set up 4 parentheses just to keep me organized here. And then I plug in what I need to. So in the first parentheses is the derivative of the first function. So that's 2x. In the second parentheses is the original second function, cotangent 9x. In the next parentheses is the original first function. The way I think about that is I think about those 2 functions. The order is flip-flopping. All right, in our last parentheses here, we are going to now take the derivative of cotangent 9x. Okay, so let's again think about this for a second and realize that we have chain rule here because it's not just cotangent x, it's cotangent 9x. So the derivative of cotangent is negative cosecant squared. We're going to keep the 9x in there, but we need to multiply by the derivative of the inside, so times 9. So for this portion here, the cotangent, highlight that here, for cotangent 9x, the derivative is all of this. Okay, the derivative of cotangent is generally negative cosecant squared. We keep that 9x in there, but we need to multiply by the derivative of it because of the chain rule. Okay. If you want, we can just clean this up slightly with getting rid of some of these parentheses so it doesn't look so cluttered. So I have y prime equals 2x cotangent 9x. Over here, I have minus 9x squared cosecant squared 9x. All right, for number 9, I have sine squared of 2x. Here's what this really looks like if we don't remember the notation for squaring a trig function. This really looks like the sine of 2x squared. So just like in that last problem, and I had you think about what's different, I want you to also think about that here. What is different about number 9 compared to the other problems that we have seen? It will help if you look at this new version that I wrote over here. Hopefully you're noticing that there are 2 sets of parentheses in this problem. So that basically means that we are going to have to do the chain rule twice. So this, I'm just going to make a note, is a double application of the chain rule. And you can recognize when this is going to happen is because there's 2 sets of parentheses. Notice there's parentheses around 2x, 2 to the x, and then a parentheses around the sine of 2 to the x. So here's how it works. We start on the outside. The outermost element here is that power of 2. So according to power rule, we bring that down, subtract 1 from the exponent, which would just make it 1. Then the innermost, or excuse me, the middle function would be sine. The derivative of that is cosine 2 to the x. And now we do the innermost. So the innermost function is 2 to the x. The derivative of that is 2 to the x ln 2. And there's our derivative here. So I just want to make some notes before we go on to another problem. So first we basically did the derivative of the outside. Then we basically did the derivative of the middle. And then we basically did the derivative of the innermost function. In this case, that was 2 to the x. All right, number 10, h of x equals, we have the square root of x squared minus 4 to the 5th. I am going to rewrite this here as x squared minus 4 to the 5/2. And I see that this is not a double application one. Okay, there's only one set of parentheses. It reminds me of some of the others we've seen where there's a power on the outside, so we're going to do power rule. Subtract 1 from the exponent times the derivative of the inside, which would be 2x. Now let's clean this up to mirror the formatting of the original problem. So in the numerator, I have 10x, right, the 5 times the 2x, times the square root of x squared minus 4 cubed all over 2. All right, 2 more to take a look at here. 11, here's an example where we're going to combine the quotient rule with chain rule. So for quotient rule, I set it up somewhat similar to the product rule one from before. I do have those 4 parentheses, but I have a minus sign between them now. And on my denominator, I have a parentheses squared. All right, in my first parentheses is the derivative of the numerator, that's negative 4, times the original denominator, minus the original numerator, times the derivative of the denominator. So the derivative of e to the pi x. Notice here it's not just e to the x. We're going to have to do chain rule here. So this is e to the pi x times pi. And our denominator is always whatever the original denominator was squared. I'm just going to slightly clean this up. So I have negative 4 e to the pi x plus, right, because I have minus a negative, 4 pi x e to the pi x over e to the pi x squared. If I wanted, I could also start factoring this numerator and try and cancel out terms with the denominator, but I'm just going to leave it like this. All right, for our last question here, we have f of x equals the tangent of the square root of 7x. All right, I'm going to rewrite this here as tangent of 7x to the 1/2, but we're taking the tangent of all of that. So notice my double parentheses when I rewrite this. So this is our double chain rule again. So the derivative of the outside, the derivative of tangent is secant squared. I'm just going to write it as radical 7x. Then the derivative of the middle has that 1/2 power. So I'm going to bring that down. Subtract 1 from the exponent, and then the derivative of the innermost, which would be 7. All right, we can slightly clean this up. So let me get my notation in here. So this is equal to 7 secant squared radical 7x over 2 times the square root of 7x. And that concludes this video on the chain rule.